The problem we are going to solve today is the kth factor of n. This is a fairly easy problem. You are given two positive integers n and k. Here they have defined the factor. What is a factor? And consider a list of factors sorted in ascending order, return the kth factor. So basically, you this is a very easy problem to solve in like big of n time complexity. Like what you can do? Uh, let's say you have given n equal to like what 17. So what are the possible factors of 17? They may reside between 1 dot 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 1 2 3 4 7. These are the candidate factors, right? And you can check one by one and then deduce whether that's a factor or not. Then you just need to find the kth factor in ascending order. So if you start from 1, then you check one by one, then you will find the factor. For example, n equal to 12, you will try from 1. Is 1 a factor of 12? Yes, it is. So it is the first factor. Fine. Then 2. 2 is a factor of 12? Yes, it is. So it is the second factor. In this way, 3 is a factor. So it is the third factor. What is the fourth factor of 12? 4 is the fourth factor of 12. Is 5 a factor? No. So it's the fourth factor. 5, 6. 6 is a factor. So 6 is the 5th factor of 12. So if your question was to find out the 5th factor of 12, then the answer should be 6. Okay. So you have to divide 12 by each of these possible potential factors 1 2 3 4 5 6 and then determine whether that's a factor or not. So this is basically one big of n solution. We need to do better. How can we do better? Because we know that every integer n has a factor less than equal to root n. Okay. Fine. Every integer n has a factor less than equal to root n. Even in prime, that factor is what? 1. Okay. How do we know this? Because if we can express n equal to a into b, where is a factor, b is another factor. If a and b both were greater than root n, then ab would have been greater than n, which is not possible. So at least for a factor, every factor, the pair must be, at least one pair must be less than equal to root n. Okay, between a and b, at least one of them has to be less than equal to root n. Okay. So we don't need to, like, for computing the factors of n, we don't need to go from 1 all the way from n. We just need to go from 1 to root n. If that is root n, then we will go from 1 to root n and we'll check this, whatever the numbers are lying between 1 and root n, and we'll check whether there's a factor or not. Okay, so if we can find a factor, let's say for 12 we are getting 2. Okay, 2 is a factor of 12, and we'll find a pair also. What's a pair? That's 6. Okay, then after 2 we'll find 3. For 3 we'll find 4 as a pair. Then 3 we can we'll like stop here because root 12 equal to 3 point something. Okay, so 1 into 12, 2 into 6, 3 into 4. This is the like approach. So the time complexity will become big of root n. We will start from 1, we'll go to root n, and these are our candidate factors. Candidate factors lie here, and for every candidate factors we will find the other pair. The other pair is nothing but n divided by I. That's the other pair. Okay. In case of if the number is a square number, like 64, okay, we need to go from 1 to 8. Is 1 is a factor? Yes, it is. 2 is a factor? Yes, it is. 3 is a factor? No, it is not. 4 is a factor? Yes, it is. 5 is not a factor. 6 is not a factor. 7 is a factor? No. 8 is a factor? Yes. So these are the factors. We get 1, 2, 4, 8. And the number 64 was there. N equal to 64. We compute each of these factors, like from 1, starting from 1. and we get another pair. What is the pair of 1? That is 64. What is the pair of 2? That is 32. What is the pair of 4? 16. What is the pair of 8? 8. Okay, so we just need to go from 1 to root n and we get the pair also. Fine. And what if k was like 2? The answer would be 2. What if k was 5? The answer would have been 1, 2, 3, 4, 5. But you can see that 8 and 8 are duplicates, so you cannot take it. You have to go here. So if k is equal to 5, the answer was 16. If k is 5, the answer is 16. In this approach, we can solve this using just big of root n time complexity, and we need big of k space. Why do we need that? Because when we traverse here from here to there, like this is I equal to 1, this is I equal to 2, this is I equal to 3, this is I equal to 4, k equal to, but if k was 5, we could not find our factor here. You can see that. You see, our factor wasn't there. Our factor was in this pair portion. So we just need to store the pairs. Okay. So the approach is this: we go from one factor to another. We get one factor and we decrease k by 1. We decrease 1. Okay. When k reaches 1, then our answer is found. But if we traverse this portion, and k does not become equal to 1, then we need to go to check this portion. Okay. And one interesting property about this portion is that this is like sorted in descending manner. Yeah, because when one factor is like very little, the other is very high, so this portion is kind of sorted in descending order. So we're gonna traverse from here, from left to right in this manner, and we're going to store the pairs in this another temporary array, and we will like go from back to the front. That kth item is our answer. I'll show the solution. So here we are going to store the factors, the pairwise factors, and going from I all the way up to root n, and we are checking the factors here. We are decreasing k one by one. At each time we are getting a factor. Then if k equals to 1, that's our factor. Otherwise we are going to just append those in a data structure, in a list. And if our k is still higher than all the pairwise factors, then we have to return -1. Otherwise, from the behind, from the rear, the kth element is our answer. Okay.